Okay, this is better actually. I like this one. Okay, so yeah, this is a joint work with Beniamino Accattoli, and who is currently in Bologna, but will be soon joining in RIA at Saclay. Good for him. And with also Pablo Barenbaum, who's a PhD student in Buenos Aires. So the title of this paper should have been Abstracting Abstract Machines, but somebody here already used the title, so we had to choose a different one. So why Abstracting Abstract Machines? Because, so the general setting of the work, so it's, we have, the lambda calculus, with some reduction strategy on one side, and an abstract machine in implementing that reduction strategy. And we know that there is an extensively developed, very well developed literature on the relationship between abstract machines and explicit substitution calculi. But explicit substitution calculi do not really abstract machines in the way that that I will show you here. They are much closer to abstract machines. So they simulate abstract machines in the lambda calculus syntax. While what we are going to do here, we're going to introduce this new explicit substitution calculus, which is called the linear substitution calculus, which has actually been introduced by Beniamino Accattoli before this paper. So this calculus, as any explicit substitution calculus, it decomposes beta reduction. Namely here in only two steps. There will be just two rules, called multiplicative and exponential. I will explain to you why. And then this calculus is also equipped with a notion of structural equivalence, which is not needed by the reduction rules, but it's there. And it has the property of being a strong bisimulation with respect to those two rules. So essentially means that it commutes with those two rules. And so what happens is that so here we say now we get to the actual title of the paper. So we distill abstract machines. So what does that mean? It means that we are, so in any one of the machines we have considered, the transitions can always be partitioned, into this taxonomy, in which you have two computationally relevant transitions, one called multiplicative, the other exponential, and at least one or more computationally irrelevant transitions, which are just there for the bureaucracy. They're there because you want to look for the next radix, essentially, And the relationship between the linear substitution calculus and these machines is that computational steps are mapped, one-to-one exactly, And while the commutative, so that C is for commutative steps, evaporate, they are distilled, They disappear into this structural equivalence. And moreover, there is a linear overhead, meaning that the complexity of the machines is preserved in the calculus. If you do some reasoning on the calculus and come up with some complexity bound, since the relationship is linear, this is the bound for the machine too, for the real execution too. So the moral of the story, I guess if you understand this, you've understood the paper. It's that, so what we claim here is that we have abstract machines can be seen as, each abstract machine can be seen as a particular reduction strategy on the linear substitution calculus plus the structural equivalence, which is, you can also see it as the fact that structural machines, have a computational part, a computationally relevant part, and then there is this computationally irrelevant, this bureaucratical part, which is the search for the next radix, and this has, very deep roots in the logic that's behind all this, in the fact that when you do cut elimination, you have principal cut elimination steps and the commutative cut elimination steps, and this corresponds to what I'm telling you, to this distillation. think the time didn't.
It's okay.
I still have 20 minutes. That's very good. All right. Well. So to motivate actually to tell you about where this calculus comes from, I'm going to go all the way back to linear logic proofnets. That's where it comes from. And this talk is the last of the conference, so I'm not going to give any technical detail. I'm just trying to give information that is not in the paper. This stuff is not in the paper. Okay, so it's an advantage of coming to a conference is to hear people talking about things that are not in their paper. So otherwise, you already know. You can look in the paper. So this is where the linear substitution calculus comes from. And it's so proofnets. Okay, proofnets are, as you know or maybe don't know, are a graphical syntax for the proofs of linear logic. Okay, and so cut elimination in proofnets can be formulated by using those three cut elimination rules that I wrote there. So there is one that is multiplicative, and it just it corresponds to the fact that you have a symmetric, monoidal closed category. Then it is also symmetric. And the two bottom rules, the exponential rules, okay, there's the truly exponential rule, and then there's a sort of a garbage collection rule, okay, they correspond to the fact that the exponential modality, that exclamation mark, is a commutative comonoid, okay, so you can package things, okay, and you can duplicate them. In this case, you extract one copy of the contents of the package and leave the rest of the package, and you can erase them. Okay, that's what linear logic is about. And of course, this exponential is also a comonad, which means that you can take the Kleisli category of the comonad, and what you end up with is, as you probably know, you end up with intuitionistic logic, right? And so this is the essential equality, I guess, under linear logic. The linear is the decomposition, of the intuitionistic arrow. So the function space being, a Kleisli or co-Kleisli category is, that form. And so let's see what happens when you encode a lambda term that is, an intuitionistic proof into proofnets. Okay, so that's how a radix looks. Okay, so you have lambda x t applied to u. Okay, it looks like that. Okay, that's the proofnet that encodes that. Now, if you start doing cut elimination, okay, you will see that it strongly suggests a calculus with explicit substitutions. Okay, so let me start cut elimination. So you first apply the multiplicative rule, okay, and at the bottom there, I'm going to try to write what this would look like in a calculus. Okay, so this multiplicative rule corresponds to the creation of an explicit substitution. Okay, it's pretty clear. Then you just kind of rearrange things so that they look better. And now you start applying the exponential cut elimination rules. Okay, so you start extracting copies of the contents of the box. And so this would correspond to having that notation that a superscript L means that substitution is linear. Okay, I'm replacing U to exactly one occurrence of X. I don't know which, but just one. Okay, it's a commutative comonoid, so you can replace it with any occurrence, and then you just keep going, and at some point, okay, you just get down to having finished all the substitutions. So so you have the term with all the substitutions done, but you still have the explicit substitution right there. But now X doesn't occur free anymore, so you can garbage collect. Okay, and you end up with so now if you look at the starting term and the ending term of the reduction, you see that you have really implemented a beta reduction step. Okay, so this is typical of explicit substitutions. But what the linear substitution calculus does, it goes a bit further. So let's look at a slightly more complex example. Now you have a function of two arguments, which are applied to two arguments, and so the proofnet is that one. Okay, and so you start reducing. Okay, so you do this first multiplicative step. Okay, which you have a radix in the calculus, and you have a radix in the proofnet. So you do them. I mean, you reduce them, and now what happens is that in the proofnet you have underlined in blue, okay, you have a radix. I mean, you have a cut. You can reduce it. Okay, but in the calculus, you no longer have a radix. Okay, because now the lambda and the argument are separated by the explicit substitution. Okay, so that's no longer a radix. You're stuck. So what do you do usually? What do traditional explicit substitution do? Well, you introduce commutative reductions. Okay, that sort of make the explicit substitution percolate through the term. Okay, so you say, okay, but explicit substitution commute to lambdas. Okay, so they commute, and so it enters inside the lambda. Now I do have a radix. Okay, so now I can keep going. Okay, and of course it doesn't only commute with lambdas. It commutes with applications. It commutes with other explicit substitution. Well, when you descend into the inferno of traditional explicit substitutions, inferno because you know that it's non-trivial. I mean, if you do things naively, you end up introducing divergence, okay, with all these commutation rules. So the solution, the idea of Beniamino was to say, well, I want lambda terms to behave as if they were proof nets, okay? I want to do proof nets without telling people that I'm doing proof nets. And so what I do is that I take that, that red thing there, with the lambda separated by, and the argument separated by an explicit substitution, and I say, that's a radix. Okay, I don't care that there's an explicit substitution in between. That's still a radix. Okay, so this is the formal definition of the linear substitution calculus. And so okay, terms are as usual. Okay, you have explicit substitutions. And so just look at the left column. Okay, the call by name version, because the call by value is just a variant. Okay, so you have two rules. Okay, corresponding to the two proofnet rules. Okay, except garbage collection, which is not interesting. So you see how the radix, the multiplicative radix is. Okay, you have a function, okay, a lambda, which is maybe embedded in a list of explicit substitutions. Okay, that's what the big L is. Okay, the big L is defined at the bottom is just a list of explicit substitutions. Okay, and then you have the argument. Okay, and you just reduce as if that list of explicit substitution weren't there. Okay. And the exponential step is you have an occurrence of x somewhere, so that C is an arbitrary context. So it means it's a term containing an occurrence of x, and you just replace it with a u. Okay, and you keep the explicit substitution there. Okay. Then there are call by value versions of this, of course. Okay, where you just replace the argument must be a value. It may be embedded in explicit substitutions too. You just do the necessary. And you get so a call by value version of the calculus. Now this is a general calculus. Okay, it doesn't have a specific strategy, but what we're interested in is implementing strategies. So that's what we're going to do now. We're going to define reduction strategies on the linear substitution calculus. Okay, and this is very easy and modular to do. Okay. You start by defining classes of contexts, okay, which will be the evaluation contexts, but they will also be the contexts that you use in place of that C. You see in the, look always at the call by name column, in the exponential rule, there is that C there, okay, which is arbitrary in general, but when you're implementing a particular reduction strategy, that C will not be arbitrary, it will be one of those contexts there, okay. And so call by name, you have call by name context. I mean, you never reduce under lambdas, of course, in no case. Then you have call by value either left to right or right to left. And you have also call by need, okay, which is, you see, call by need essentially is just it's the call by name context plus there is an extra case that tells you that you can reduce inside an explicit substitution if you need the value of x. You see, you're evaluating a term. At some point you get to x, okay, you have that n prime of x, and well, you have to go and look into the explicit substitution, because maybe it's not a value, and you have to normalize. And then you define the calculus by picking the two versions of the multiplicative and exponential rules. You just pick the versions that you see fit for the strategy. So call by name, of course, you choose the by name version of both rules. Call by value, you choose the by value version of both rules. And what's interesting is call by need, in which you choose the call by name version of the multiplicative step and the call by value version of the exponential step. So let me show you again. You see, you take the top one from the left column and the bottom one from the right column. Okay, and that defines call by need. Okay, nothing else. It's very easy. Then of course you close under those contexts. I mean those the contexts that are of interest for the strategy. And okay, then I told you, so this is it, okay, you define, this is how the calculus is defined. And each of these calculi is equipped with the structural equivalence. Now I just write a few axioms. So for example, you have garbage collection, okay, if X no longer appears in T, then you can get rid of the explicit substitution. And then you see the fact that the explicit substitutions commute with respect to applications. Okay, that's what usual traditional explicit substitutions do. Here we don't need it to define the calculus. It's just an equivalence. Okay, and then you can prove that that's a strong dissimulation. Okay, in all cases, I mean, you have every calculus has its own version of the structural equivalence, and every time it's a strong dissimulation. So I come to the main concept, the technical concept, but I will not give any technical detail. It's just the definition. Okay, what is a distillery? So a distillery is so you choose deterministic rules. Okay, in our case, of course, it would be one of those four choices. Okay, those four choices of rules. And a structural equivalence, which you have to make sure that it's a strong simulation. Then you choose an abstract machine, okay, on the other side, and this abstract machine you have to partition. It has to have a sort of a taxonomy, of its transitions into two classes. So one computational class, which is itself composed of two kind of transitions, multiplicative and exponential, and another class of commutative transitions, and then you define this decoding function that is such that multiplicative steps of the machine are mapped to exactly one multiplicative step of the calculus modulo the equivalence. Same thing for the exponential steps, and the commutative steps just evaporate. Okay, they are distilled; they become just equivalents. Okay, so the moral of the story is that so if you take a term, okay, a lambda term, okay, and you start a pure lambda term without explicit substitution, and you start evaluating it in one of the the strategies of the linear substitution calculus, what you're doing essentially is that you are doing the same thing as the machine, as the absolute machine would do, modulo the fact that you're forgetting the commutative transition. Okay, and so there are many distilleries, okay, as we all know, so for call by name you can do this with the Cruvin machine and with the variants of it. So this is all in the paper, okay, and with the CEK, with the SECD for the left to right call by value, and then with a very simplified version of the Zik machine. So just essentially the right to left skeleton of call by value. And the zinc itself, I mean, it's as you know, I mean, it has many optimizations, things that we do not cover. And then for call by need, you have a couple of well-known machines for call by need, like the lazy green machine and a machine introduced by Sestov. Okay, they can all be distilled, okay, in this way. And in all cases too, we have this important result is that the distillation preserves the complexity. Okay, so the number of commutative steps that you forget when you reduce. So suppose that you have your term T, okay, and you reduce it in your linear strategy, okay, in L steps to a normal form T prime. Okay. Now I told you that this means that the abstract machine that corresponds to the calculus does at least L steps. I mean, actually, it does exactly L commutative steps. But how many? Computational steps. But how many commutative steps does it do? Okay, the calculus doesn't see that. Okay, it forgets that. Well, it does a number which is big O of the length times the size. Okay, so it's linear in both the length and the size of the term. Okay, and yeah, I guess I'm done. Just one thing that I want to say, I want to conclude with is so of course there is a huge literature on explicit substitutions and abstract machines, and for example, the work of Olivier Danqui and many other people, co-authors. So it is largely, for the most part, it's unrelated to what we are doing, because for example, they show how to extract machines from functional evaluators. They have one thing that is related is a deconstruction of the SECD machine, which is kind of maybe similar to this distillation that we're doing, but not exactly. Then, of course, they do a much deeper analysis of the zinc machine that we do not do. And in any case, they always use traditional explicit substitutions. There is no connection with the linear logic ever mentioned. Okay? And about linear logic, about the linear substitution calculus, so as I told you, it was introduced by Beniamino Cattoli, but from previous work with Delia Kessner, and also, Delia Kessner and other people like Stéphane Langrand, I'm sure, but I don't know, there must be other people too, who essentially, the people who noticed these things, that they said, okay, proof nets are essentially doing explicit substitutions, okay? And I'm sure that this has been noticed like way, early, like probably maybe even in the late 80s or early 90s, I don't know. And then, so that's not at all new, okay, of this work. And also, this calculus bears, in case you wonder, bears some resemblance with calculi that have been introduced previously, that by even back to De Bruyne in the 80s. But none of those calculi is really, is exactly this calculus, okay? And then, of course, for code by need, okay, there is it's a nice the code by need version of our calculus. I think it's a nice formulation of code by need, which is kind of similar, to recently reformulated, code by need calculus. And it has no reassociation axioms, unlike, which is a sort of a maybe small defect of the original formulation. So thank you, I stop here.
Questions?
Michael Adams, University of Utah. You might have stated, I just missed it. You've got the two choices for the exponential and the multiplicative. What's the fourth combination correspond to?
The fourth combination. Yeah, that's an interesting question. We don't know. It's I don't know. It's a weird thing in which you evaluate being called by value. I mean, morally called by value, but then you do substitutions. Even when it's not a value. I mean, it's a very strange thing. It's like, I don't think it corresponds to anything, because you see what it tells you, what it will tell you. You see the M from the right-hand side would tell you that you can only create an explicit substitution if the argument is a value, morally, okay. But then, I guess, but then when you, on the right-hand side, you can apply that always. So, no, actually, no, I guess no, it's just called by value. Yeah, it would just, because you see, you never create substitutions which have no values. So it's a sort of I don't know, mutilated code by value. I know you have to also to define the context, which context you use. So I don't know. I mean, it's not something that we've looked into it. I don't know. It's something that it would be a bit strange. I don't know. But it's an interesting thing to look at.
Yeah. So firstly, great talk. I like the idea of doing my computations in a distillery. Could you go to the next slide?
Yes.
This is sort of a follow-up to the previous one. So, yeah, firstly I wanted to ask about what's the fourth combination, but you've answered that. So I was wondering if you've got a sort of nice periodic table thing going on with the two different reduction relations, but I was wondering if there's some order you can bring to these seemingly arbitrary evaluation contexts.
Yeah, that's also something that we have started to look, but I don't have a definite results or anything. But yeah, you see how it's so essentially what you do in those contexts. Okay, you are telling the machine where to look for the next radix. Okay. So you can do all sorts of things, you know, with by just, you know, adding cases, you know, like you know, you can mix things and you can say, oh, okay, you know, I can go. Oh, you can even do, for example, non-deterministic machines. Okay, you can have context, okay, that you know, that can evaluate the left or right, you know, and you can do both. So you can have a machine that can choose, you know, whichever it wants. It's so I would say that at some point the choice is limited by the fact that maybe you want your strategy to be deterministic, okay? Because it's something that I haven't said, or maybe I said it very briefly, but these contexts guarantee that the strategy is deterministic, okay? There's only one way to reduce a term under these strategies. But you can devise, you know, more liberal strategies in which it's not deterministic anymore. But it's still, in some cases, it's not deterministic, but it's morally deterministic because you have like the diamond property of one-step reduction. So essentially, it's like as if it's really deterministic, where your choices don't really matter. The length of a reduction is always the same, no matter what choices you do, you make. So, so yes, you know, there is a gradient, but you know, we don't have, you know, a really, you know, like a taxonomy, you know, a very in-depth study of this for the moment.
So you said the length is always the same regardless of which redex you choose then?
Sorry?
The length of the, like...
yeah, when you have that property. I mean, when you have, you can have non-deterministic strategies, okay, in this calculus. Not all of them are like that, but okay, but some of them can be, can have this property that you have the diamond property in one step. I mean, you just, if you diverge, you go back in exactly one step, okay? Which means that, you know, when you have this property, it's a standard thing of rewriting theory, you know, any reduction, you know, to normal form, for example, has the same length, okay? You cannot do more work, okay, because, you know, you have the diamond property.
Are these contexts, are they maximally liberal? If you added anything to them, would it go wrong, or?
No, the ones I'm talking about, no, they would be, you can liberalize even more and then get, you know, complete non-determinism.
Sorry,
I mean, the most liberal choice is to take context to be anything. You know, that C there, you know, can be the evaluation context and also the context that it's there in the rule. And in that case, you have a calculus which is, you know, which has no strategy whatsoever. Just you can reduce radixes wherever you want, and it's completely non-deterministic. I mean, sorry, in the sense that, of course, it's confluent. It's always confluent, okay. But choices matter in the sense that, you know, you can have reductions that are very long. You can diverge with some reductions and not with others, okay. While when you have strong confluence, either you converge or you diverge. You know, you see what I'm saying? It's like much more.
Yeah, sorry. I actually meant sort of maximally liberal for deterministic.
So yes. Sorry. Oh, sorry. Yes. Sorry. Yes.
So if you add anything to those contexts, then suddenly.
Yes. That's sorry. Yes.
Okay.
So, yeah, Jakob Johansen, Aarhus University. So first of all, I'd like to add a comment to what you just said, which is that if you have unique decomposition, if your contexts give you unique decomposition, then the reduction strategy is imposed by the grammar of contexts. Whereas if you have a more liberal context description, you will still be able to impose determinism if your reduction strategy is just, you know, if the function that implements the reduction strategy is a function. So it's not necessarily imposed by, it doesn't have to be imposed by the grammar of context. Nevertheless, so I have two questions. The first one is, you compare your work to the work of Danby and others. One of the things about the syntactic correspondence of Danby and others is that it's an entirely mechanical process to get from a reduction semantics to an abstract machine. Not necessarily to a canonical abstract machine, but to an abstract machine in the form of a transition system. So I was wondering if you could elaborate on would it be possible to implement this distillation as a mechanical process? Like, would it be possible to implement it as an algorithm?
Yes, that's very interesting. Yes, I don't know if there is an algorithm, but
I noticed that you require bi-simulation proof in order to make it sound.
Yes, that's for having, but that's when you already have a machine and you want to simulate it. Okay. So in general, you know, if you just have a choice of contexts and and rules, I mean, I have, I know how to do it by hand. Okay, if you give me, you know, a strategy, I can construct a machine that does that.
So the thing about making it mechanical is that if it's mechanical, then we're certain it scales.
Mm-hmm.
Whereas if we have to do it by hand, we cannot be sure that maybe there is a larger problem for which there is no solution to it. Mm-hmm. And that's sort of my interest in this. So the second question has to do with in fact, the exponential rule that you have on the slide there. Mm-hmm. So as I read that rule, you have to find a free variable inside some context.
Yes.
Okay. So I was wondering, how does that process of finding a free variable, how is that present in the abstract machine that you distill? Because that takes time. That's not a one-step process.
Yes, absolutely. Yeah, it's the essentially those are those commutative stuff. I mean, it's the fact that you start entering into the term, okay, and then you use a stack to remember where you are. Essentially, so the one nice thing of after, I don't know, seeing this work that I have understood, but probably I don't know, it's well known, is that essentially what the machine does is it builds that C there, okay. It gradually builds that C mm-hmm. just by exploring the term and putting aside in stacks and environments, whatever, what's around the variable, and then at some point it gets to the variable and it does.
Right, but don't you need to go back to the root of the next redex in order to find the next explicit substitution? I mean, it just sounds like you're not that you can't limit yourself to a linear overhead. It sounds like it becomes exponential or polynomial anyway.
No, it's.
I mean, it just sounds like that.
No, okay, okay. The thing is not. It's not that the machine is not implementing, like I mean, naively this search, this exponential reduction. I mean, the machine is doing what it does usually.
Yeah.
Okay.
But you get to the abstract machine somehow. You extract the abstract. You distill the abstract machine somehow.
Yes.
So somewhere getting back to the next explicit substitution that you want to handle, and then finding the next free variable. Somehow those steps must have been eliminated somehow.
Yes,
I don't see where they've gone.
Well, take for example the Krivin machine, which is probably the simplest. Okay, for this case, and okay, the commutative step in that case is the application. Is when you push something to the stack. Okay. Well, the number of things that you can push to the stack, you can prove that it's limited by the number of steps, well, by the size of the term initially, and then by the number of of previous computational steps that you've done. Okay, there is a sort of amortized analysis, okay, that you do, in which you can never, if you have something, if you push something on the stack, it means that you have done something computational at some point.
Okay, yeah.
So that's what makes it linear. You don't need the really amortized analysis in the case of the Krivin machine, but you do need it for the call by need machines, which are much more complicated. And in fact, you will see in the paper there is an amortized analysis argument. Okay. So it's complex. Yeah, you're right. I mean, I agree with you that it's not immediate. Yes.
Okay, thank you.
Let's thank the speaker again.
Okay, we will close with some lightweight presentations, and we will start with the Student Research Competition Award. And if all is well, make one